Hello viewers, welcome to online course on Mathematics 3, and this course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the Poisson distribution, and this is the special type of distribution of probability theory. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities, Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. Before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about some special type of distributions, that means the binomial distributions. Okay. So in this chapter we have discussed about the introduction of a binomial distribution and the definition of a binomial distributions as well. And you know the binomial distribution is a discrete distribution. And there are two special type of discrete distribution. First one is binomial distribution and the second one is Poisson distribution. So today we are going to discuss about the Poisson distributions. So after that we have discussed about some theorem on binomial distributions and mean of a binomial distributions as well as the variance of a binomial distribution. And then I have given some related examples on binomial distributions. So today we are going to discuss about the special type of distributions, and that means the Poisson distributions. Okay. So this is and this part is on the probability theory, you know. So in this section we will continue to discuss about the definition of a Poisson distributions. After that we will talk about some cases where the Poisson distributions are fit. And then we will talk about some theorem on Poisson distributions, and then we will study on the binomial approximation to the Poisson distributions, and after that we will discuss some related examples on Poisson distributions. Okay, so this is my today's lecture, or the sixth lecture on the probability theory. So the content of this theory, first we will define the Poisson distributions, then some theorem on Poisson distribution we will discuss in this lecture, and after that we will continue to discuss about some examples on Poisson distributions. Let us begin with the definition of Poisson distributions. Okay, so here is the definition. A discrete random variable capital X is said to have a Poisson distribution with parameter mu greater than 0. So in that case where the parameter is only mu and mu is greater than 0, but in a binomial distribution, you know, there are two parameters n and p. Okay, and p lies in the interval 0 to 1 and n be any positive integer. So in that case, in a Poisson distribution, mu is greater than 0 if its distribution is given by x, and this is the discrete distribution, you know. So here the sample points are 0, 1, 2 and up to infinity, but in a binomial distribution there are n sample points, but in a Poisson distribution there are infinite number of sample points, and the corresponding fi are f0, f1, f2 and up to infinity. Okay, so where the probability mass function fi is equal to probability of x is equal to I, and this is equals to e to the power minus mu into mu to the power I by factorial I. Okay, so in a Poisson distribution, you know, the probability mass function, and it will be e to the power minus mu into mu to the power I by factorial I at x is equal to I. On probability mass, say f2, so in that case we will take I is equal to 2. So therefore in a Poisson distribution, and it will give e to the power minus mu into mu square by 2 factorial. Okay, this is called a Poisson distributions. This is the particular example of the Poisson distribution, you know. If we take I is equal to 3, then the probability distribution function, and it will give f3, and f3 is equal to e to the power minus mu into mu to the power 3 by 3 factorial, and so on. So therefore there is a note on Poisson distribution. The first note, it will be, since the parameter is mu greater than 0, so therefore Fi is equal to probability of x is equal to I, and this is equals to e to the power minus mu into mu to the power I by factorial I, and it is greater equals to 0 when mu is equal to 0, as well as summation over I is equal to 0 to infinity Fi is equal to summation over I is equal to 0 to infinity e to the power minus mu by I factorial into e to the power mu to the power I, and this is equals to e to the power minus mu. So e to the power minus mu is a constant while mu is a parameter, into summation over I is equal to 0 to infinity mu to the power I by factorial I. And this is the infinite series of the exponential function, that means e to the power mu. So e to the power minus mu into e to the power mu, and this is equals to 1. Okay, so this is the fundamental properties of the probability mass function. So all Fi is greater equals to 0, and summation over I is equal to 0 to infinity Fi is equal to 1. So the Poisson distribution is satisfied both the fundamental properties of the distribution function, Fi is greater equals to 0, as well as summation over I is equal to 0 to infinity Fi is equal to 1. Okay, so after that we will take the another properties of the Poisson distributions. When the random variable capital X has a Poisson distribution with parameters mu greater than 0, then we can write it X equivalent to probability of mu. Okay, and we say X is a Poisson variant in that case. And I have already mentioned in the previous class where the X capital X, the binomial variant X is equivalent to V of n comma p. So in that case mu is only the parameter, so in a Poisson distribution it can be written as X equivalent to p of mu. Okay, so where mu X is the Poisson variant. And number 3, the Poisson distribution is a limiting case of binomial distributions, where n is very large and p is a very small, so that mu is equal to np is a finite magnitude. So in a binomial, p is a very small quantity, and p lies in the interval 0 to 1, and n is a very large quantity, that means n is tends to infinity. But in a Poisson distribution, the limiting case of binomial distribution it is actually, and when n is very large and p is very small, so that mu is equal to n into p. Okay, and the significance of the parameter mu is given in the next theorem. But now we will move on the next slide. So in this slide we will discuss about the some cases where the Poisson distributions are fit. Let us consider a sequence of changes if the random variable x of t denotes the number of changes during the interval 0 comma t. Okay, so then x of t assume the value 0, 1, 2 and up to infinity. In a Poisson distribution there are infinite number of sample points. Okay, so it can be shown that probability of xt is equal to I, and this is equals to Fi. And in that case, where the probability mass function Fi, and it will give e to the power minus lambda t into lambda t to the power I by factorial I. Okay, so where I is equal to 0, 1, 2 and up to infinity. And lambda is the number of changes per unit time, and mu is equal to lambda into t. So thus the distribution of x of t, and it becomes x such that 0, 1, 2 and up to infinity. So there are infinite number of samples in a Poisson distributions, and the corresponding Fi are f0, f1, f2 and up to infinity. So while the probability mass function Fi at xt is equal to I, so in that case where x is equal to xt, and xt is lies in the interval 0 comma t. Okay, and xt is the number of changes during the interval 0 comma t. And I have discussed in the previous slide where capital X is the variant. Okay, so in that case where the capital X of t is lies in the interval 0 comma t. Okay, so probability mass function of fi is equal to probability of xt is equal to I, and it will give e to the power minus lambda t into lambda t to the power I by factorial I. So where I is equal to 0, 1, comma 2, comma 3 and up to infinity. So which is the probability mass function of the Poisson distribution as well. Okay. So there are two types of probability mass function of the Poisson distribution. First one is probability x is equal to I. So in that case, where x is the random variate, okay, and it is equals to e to the power minus mu into mu to the power I by factorial I, where mu is the parameter. But in that slide we are seeing that xt is the random variable, and it is the number of changes during the interval 0, t. And probability of the mass function, probability of xt is equal to I, and it will give e to the power minus lambda t into lambda t to the power I by factorial I, where I is equal to 0, 1, 2 and up to infinity, and which is also the Poisson distribution, where the probability mass function is this, okay, and lambda is the number of changes per unit time. So therefore the changes of the interval is a Poisson variate with the parameter mu is equal to lambda into t, and this is actually the average changes in the interval 0, t. So there is a note on the distribution function, that means Poisson distribution is where the Poisson distribution is fit. So the interval 0, t may not be the time interval in that case, and we use the notation xt in place of x because it depends on t. So I will take an example on the cases where the Poisson distribution is fixed. So let a used metal sheet be produced by a machine in a factory. Defect are noticed in the sheet. The machine is such that the average number of defects per unit area is 3. A pieces of 10 unit area of the sheet is purchased by a company. So here capital X is equal to number of defects in this piece. Then X may assume the values 0, 1, 2, 3 and up to infinity, and X is the random variable. So here changes means defect, and the interval 0, t stand for 10 units area of the sheet, or 0, 10. So and I have already mentioned in the previous slide where the Poisson distribution is fit. So in that case where the changes means the defect, and the interval 0, t stand for 10 units area of the sheet, that means 0, 10. So after that the Poisson distributions function, and it can be written as x such that 0, 1, 2 and up to infinity, and corresponding fi, and it will be f0, f1, f2, okay, and corresponding to 0, corresponding to 1, corresponding to 2 and up to infinity. So where the probability mass function fi is equal to e to the power minus lambda t into lambda t to the power I by factorial, okay, and with the parameter mu is equal to lambda into t, where lambda is equal to 3 and t is equal to 10. So 3 into 10, that is 30, and 30 is the average number of defect per 10 unit area of the sheet. Okay, so therefore probability of x is equal to 0, that means f of 0, the f0 is the probability mass function, okay, at x is equal to I, at x is equal to 0. So and it is equals to e to the power minus 30. So mu is equal to lambda into t, and lambda t is equal to 30. So e to the power minus 30 into 30 to the power 0 by 0 factorial. That means e to the power minus 30, where 30 to the power 0 is equal to 1, the power of any finite value is equal to 1, and 0 factorial is equal to 1, so that is, this is equals to e to the power minus 30. So therefore the probability of no defect in the piece is equals to e to the power minus 30. In the other word, 100 into e to the power minus 30% such pieces will be free from defects. Okay, so therefore the number of deaths in a state in 1 year is a Poisson variate. So when the Poisson variate are used, so in that case the number of death in a state in 1 year is a Poisson variate. The number of ratio active atoms decayed in a time t follows the Poisson distribution with parameter mu is equal to lambda t. That means the average number of decayed radioactive atoms per unit times. So in that case, where we can use the Poisson variant or Poisson distribution, where the probability mass function e to the power minus lambda t into lambda t to the power I by factorial I, or e to the power minus mu into mu to the power I by factorial I, where mu is equal to lambda into t. Capital X of t is a random variate and it is lies in the interval 0 comma t. Now we are going to the next slide. So there are some theorems on Poisson distributions. So if X is a Poisson variate with parameter mu, in that case where the parameter is only mu. So then the mean of X is mu as well as the variance of X is mu. So in a Poisson distribution, the mean of a Poisson distribution is mu as well as the variance of a Poisson distribution is mu. So here is the proof of the given theorem. So the value assumed by X are 0, 1, 2 and up to infinity, and in a Poisson distribution with probability function fi is equal to probability of X is equal to I, and it is equals to e to the power minus mu into mu to the power I by factorial I. And this is the Poisson distribution, and the probability mass function of a Poisson distribution, it will be this, okay, e to the power minus mu into mu to the power I by factorial I. So now we are going to find the mean of a Poisson distribution. Okay, so mean of a Poisson distribution, this is the definition of mean. It is equals to summation over I is equal to 0 to infinity I into fi in a discrete case, where fi, the probability mass function fi is equal to e to the power minus mu to the power I by factorial I. So after putting the value of fi on that summation, and it will give summation over I is equal to 0 to infinity I into e to the power minus mu into mu to the power I by factorial I. And after cancelling the term I on numerator and denominator, and it will give I minus 1 factorial, the denominator will give I minus 1 factorial. And if we take e to the power minus mu and mu as common, then from this summation it will give mu into e to the power minus mu. Okay, this is the constant term. Summation over I is equal to 0, 1 to infinity mu to the power I minus 1 by I minus 1 factorial. Now expanding this summation, and from this we will get the first term, it will be mu to the power 0 by 0 factorial, and second term it will be mu to the power 1 by 1 factorial, third term it will be mu to the power 2 by 2 factorial if we put n is equal to, if we put I is equal to 3, okay, and after that mu to the power 3 by 3 factorial up to infinity. So there are infinite number of terms. So after simplifying this series, and from this we will get mu into e to the power minus mu into 1. So the first term it will be 1, second term it will be mu, third one mu square by 2 factorial, fourth term it will be mu to the power 3 by 3 factorial and up to infinity. And this is the series of the exponential function, that means e to the power mu. So mu into e to the power minus mu into e to the power mu. So after cancelling the term e to the power minus mu and e to the power mu, and from this we will get mu. So therefore mean of the Poisson distribution and it will give mu. Okay. So after that we are going to find the variance of the Poisson distribution. Okay. So first of all, the variance of x in a distribution function, and it will give expectation of x into x minus 1 minus m into m minus 1. This is one of the properties of the variance of x, and where m is the mean of the random variable capital X, and it is denoted by e of x. Okay, and the mean of the distribution function, and it is actually mu, and I have already found in the previous slide the mean of the Poisson distribution, and it will give mu. So now we are going to find the variance of x, and variance of x is equal to expectation of x into x minus 1 minus m into m minus 1, where expectation of x into x minus 1, and it will give from the definition of the expectation, summation over I is equal to 0 to infinity I into I minus 1 into fi. Definition of expectation on distribution function. Okay, so here fi is equal to, in a Poisson distribution, e to the power minus mu into mu to the power I by factorial I, and therefore this summation will reduce to summation over I is equal to 0 to infinity I into I minus 1 into e to the power minus mu to the power I by factorial I. And after cancelling the term I into I minus 1 on numerator and denominator, then the factorial I, it will give I minus 2 factorial. Okay, so I factorial is equal to I into I minus 1 factorial, or I into I minus 1 into I minus 2 factorial. Okay, this is the properties of the factorial function. And from this we will get mu square into e to the power minus mu into summation over I is equal to 2 to infinity mu to the power I minus 2 by I minus 2 factorial. So e to the power minus mu is a constant term as well as mu square is a constant term. And summation over I is equal to 2 to infinity, it is mu to the power I minus 2 by I minus 2 factorial, and this summation will reduce to mu by 0 factorial when we put I is equal to 2 in that section. We will get mu to the power 0 by 0 factorial, and if we put I is equal to 3, then we will get mu to the power 1 by 1 factorial. If we put I is equal to 4, then it will give mu square by 2 factorial. Okay, so up to infinity. And after simplifying, we will get 1 plus mu square by 2 factorial plus mu 2 by 3 factorial and up to infinity. And this is the exponential series, and it is equal to e to the power mu. So mu square into e to the power mu into mu e to the power mu, and after cancelling the term e to the power minus mu and e to the power mu, and it will give 1. So that means expectation of x into x minus 1, and it will be mu square. Okay, after simplifying this we will get mu square. So therefore from the properties of a variance function, so variance of x is equal to expectation of x into x minus 1 minus m into m minus 1, where m is the expectation of x, that means mean. And I have already found in the previous slide where the expectation of m and the expectation of capital X, and it is actually mu. So from that we will get expectation of x into x minus 1, so it is actually mu square minus mu into mu minus 1, and after simplifying it we will get mu. So therefore the variance of the Poisson distribution, and it will also give mu. So therefore the mean and the variance of a Poisson distribution, and it will be mu, and the standard deviation of a Poisson distribution, and it will give root over of mu. So in light of the above theorem, we considered the parameter mu is equal to lambda t. So if we put a mu is equal to lambda t, so similar thing will happen. That means mean and the standard deviation of a Poisson distribution, where mu is equal to lambda t, and it will give lambda t. Okay, where xt is the random variable and is defined in the interval 0, t. Let us move on the next slide. So in this slide we will discuss about the binomial approximation to Poisson distributions. Okay, so the range of applications of Poisson distributions becomes more wider as it is used as an approximation of a binomial distributions. So in case of a binomial distribution where n becomes large and p is small enough, so in the binomial distribution where n is a positive integer and p is a number where lies in the interval 0, 1. So n is a very large integer and p is a small enough, so that np is a moderate fixed value. So in a binomial variate, the becomes approximately equal to the Poisson variate, and this is given by the following theorem. Okay, so let the random variable capital X follows the binomial distribution with probability mass function, and this is the probability mass function of the binomial distributions. If I is equal to probability of x is equal to I, and this is equals to NCI into p to the power I 1 minus p whole to the power n minus I, where I is equal to 0, 1, 2 and up to n. And n and p are the parameters of a binomial distribution, and if n tends to infinity and p tends to 0, such that np is equal to mu. Okay, and mu is the parameter of the Poisson distribution, and np is equal to mu, a fixed quantity, then in limit n tends to infinity, NCI p to the power I into 1 minus p whole to the power n minus I, and it is equals to e to the power minus mu to the power I by factorial I for a fixed I. So therefore the Fi, so Fi is the probability mass function. So Fi of a binomial distribution is equivalent to Fi of a Poisson distribution. That means the probability mass function of a binomial distribution is approximate equals to the probability mass function of the Poisson distribution. Here is the example of the above theorem. Let a box contain 200 fuse. Experience tells that 2% of such fuse defect. Let us consider the experiment of drawing a fuse and testing whether this is defective or not. So in that case, while let capital number of defective fuse, therefore X has binomial distribution with parameter n is equal to 200. So in that case, where n is equal to 200 and p is equal to 2 by 100. Okay, that means 2% and 0.02. So the probability mass function of X is Fi is equal to NCI p to the power I 1 minus p whole to the power n minus I. This is the probability mass function of the binomial distribution, you know. So where p is equal to 0.02 and n is equal to 200. So after putting the value of n and p, and from this we will get 200 Ci 0.02 whole to the power I into 1 minus 0.02 whole to the power 200 minus I. So here we see n is so large and p is so small. So we can write, so in that case, you know, n is the and p are the parameters. So where n is equal to 200 and p is equal to 0.02. So n is a very large quantity and p is a very small quantity. Okay. And this is the binomial distribution, that means the probability mass function of a binomial distribution. So in that case, we see that n is so large and p is very small. So we can write it as approximate equals to e to the power minus 200 into 0.02. That means mu is equal to n into p by factorial I. So that means e to the power minus mu by factorial I. Okay, this is equals to e to the power minus 4 by factorial I. So therefore the probability of X is less or equal to 3. Okay, and this is equals to, you know, in a binomial distribution we know that, and or this is the probability theory where the distribution function probability X less or equal to 3 and it is equals to f0 plus f1 plus f2 plus f3. And from this we will get f0 is equal to e to the power minus 4 by 0 factorial, that is approximate equals to this is actually, okay, plus e to the power minus 4 by 1 factorial plus e to the power minus 4 by 2 factorial plus e to the power minus 4 by 3 factorial, where e to the power minus 4 is a fixed, okay, and which is depend on I. That means if when you put I is equal to 0, then it will be this, I is equal to 1, it will be e to the power minus 4 by 1 factorial, I is equal to 3, it will be this. Okay, so this is the probability of X less or equal to 3. So this is the example of a binomial approximation to the Poisson distributions. Okay, so where n is the very large and p is a very small quantities. So first of all, we are going to take example number 1. For a Poisson variant, if probability of x is equal to 2 is equal to probability of x is equal to 1. Find probability of x is equal to 1 or 0. Also find the mean of x, that is the random variable. Here is the solution of the following problem. Let m be the parameter of the Poisson variant or mu be the parameter of the Poisson variant. Okay, so in that problem I will take m, okay, as a parameter of Poisson variant. So therefore the probability mass function of the Poisson variant, that means probability of x is equal to I, it is equals to fi, and this is equals to e to the power minus m to the power I by factorial I. So according to the question, where the probability of x is equal to 2 is equals to probability of x is equal to 1. That means the probability mass function f2 is equal to probability mass function at x is equal to 1 or same. So from the Poisson variant, you know f2 is equal to e to the power minus m to the power 2 by 2 factorial, and f1 is equal to e to the power minus m to the power 1 by 1 factorial. So after simplifying this equation, and from this we will get the value of m, and m is equal to 2. And therefore probability of x is equal to 1 or 0, and it will give f0 plus f1 is not f1 plus f0 plus f1. And from this we will get e to the power minus m into 1 plus m. After putting the value of 0 and 1 in the Poisson variant, we will get e to the power minus m into 1 plus m. And you know where m is equal to 2, and from this equation we get e to the power minus 2 into 1 plus 2, that is 3 into e to the power minus 2. So this is the required probability, that means probability of x is equal to 1 or x is equal to 0, and the mean of this distribution, it will be 2. Okay. So after that we are going to take one more examples on the Poisson variant. So a car farm has 2 cars which it hires out day by day. The number of demands for a car on each day is distributed as a Poisson distribution with average number of demands per day is 1.5. Calculate the proportion of days on which neither car is used and the proportion of days on which some demand is refused. That means from this problem we are going to find the probability of x is equal to 0. That means the proportion of days on which neither car is used, okay, and probability of x greater than 2. That means the proportion of the days on which some demand is refused. So a car hire company manufacture 2 cars on a day. So here is a solution of the given problem. So let capital X be a random variable denoting the number of demands for a car on any day. Okay. So then X is a Poisson distribution with parameter mu is equal to 1.5 and 1.5 is given. So its probability mass function, on a Poisson distribution where the probability mass function, probability of x is equal to I, and it is equals to e to the power minus mu into mu to the power I by factorial I, where mu is equal to 1.5. So the first part of this problem, it will be proportion of days on which neither car is used, and it is equals to probability of there being no demand for the car, and it is equals to probability of x is equal to 0. So that means f of 0, and it is equals to e to the power minus mu into mu to the power 0 by 0 factorial, and e to the power mu is equal to e to the power minus 1.5, and mu to the power 0 is 1. So, and the 0 power of any finite value is 1, and 0 factorial is 1. So from this we will get e to the power minus 1.5, where e to the power minus 1.5 is equal to 0.02231. Okay. This is the required probability of there being no demand for the car, or the proportion of the days on which neither car is used. And after that we are going to solve the second part of the problem, and it will be proportion of the days on which some demand is refused. And this is equals to probability for the number of demands to be more than 2. So the car hire company manufacture 2 cars in a day, and after that they refused the demand. Okay, so that means the probability of days on which some demand is refused, and it is equals to probability for the number of demands to be more than 2. That means probability of x greater than 2. And it is equals to, from the definition of the probability or the distribution function, it will give 1 minus probability of x less or equal to 2. And it is equals to 1 minus probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2. And where probability of x is equal to 0, probability of x is equal to 1 and probability of x is equal to 2, they are the probability mass function of the Poisson distribution. So it is equals to e to the power minus mu plus e to the power minus mu into mu by 1 factorial plus e to the power minus mu into mu square by 2 factorial, okay, where mu is equal to 1.5. So after putting the value of mu, and from this we will get the required probability distribution function. We get the required value of the probability, and it is equals to 0.19126. So the proportion of the days on which some demand is diffused, and it is equals to 0.19126. Okay. So after that we are going to take one more example on the Poisson distributions. So in a certain factory turning a razor blade, there is a small chance 1 by 500 for any blade to be defective. So in a 500 blade, one blade is defective. Okay, the blades are in fact in 10. So use Poisson distribution to calculate the approximate number of packets containing no defective, one defective, and number 3, 2 defective blades respectively in one consignment of 10,000 packets, given e to the power minus 0.02 is equal to 0.9802. So there are 3 parts of the given problem. So first one, we are going to find the probability of no defective. Second one, it will be 1 defective, and third one is 2 defective blades respectively in a 10,000 packets. Okay, so here is the solution. On an average, there are 1 defective blades per 500 blades. Okay, so you know the defective blades is 1 by 500. So that means 1 blade is defective per 500 blades. So the average number of defective blades in a packet is 10 into 1 by 500. You know. So the blade are in packet is of 10, so the average number of defective blade, and it will give 10 into 1 by 500, and that means 0.02. Okay, so let capital X be the number of defective blade in a packet. Follows the Poisson distribution, you know. So with parameter mu is equal to 0.02. So in that case, where the parameter mu is equal to 0.02, that means lambda into t, while lambda is equal to 1 by 500 and t is equal to 10. So after calculating this, we will get the parameter mu on a Poisson distribution, and it will be 0.02. So after that, from the probability mass function of a Poisson distribution, and it will give e to the power minus mu into mu to the power I by factorial I. So now we are going to solve the first part of this problem, the probability that one packet contains no defective blades. That means probability of x is equal to 0. So this is equals to f0, and f0 is equal to e to the power minus mu into mu to the power 0 by 0 factorial. Okay. So from this we will get e to the power minus mu, and you know mu is equal to 0.02. So it is equals to e to the power minus 0.02. That means 0.9802. Where e to the power minus 0.02 is equal to this. So the value of e to the power minus 0.02 is given. So therefore the number of packets in the consignment containing no defective blades is 0.9802 into 10,000. So this is actually the no defective blades in one packet. So there are 10,000 packets. So in a 10,000 packet, there are the number of no defective blades 9,802. Okay. So after that, we are going to solve the second part of this problem. So this is actually the probability that one packet contains no defective blades. So I'll take first one. First of all, we are going to calculate it in one packet. So after that, we are going to take 10,000 packet. Okay. So when we take one packet and one defective blade in a packet, and it is actually probability of x is equal to 1. That means f1 is equal to e to the power minus mu to the power 1 by 1 factorial. that is mu into e to the power minus mu, and this is equals to 0.02 into e to the power minus 0.02, where e to the power minus 0.02 the value of this is given. So after calculation we will get 0.019604. So in a 10,000 packet, and we will find the one defective billets, and it will give 196.04. that means it is approximately equals to 196. So in a 10,000 consignment, so in a 10,000 packet there are one defective billets, and it will be 196. Okay. And after that we are going to solve the third part of this problem, and it will be probability that one packet contains two defective plates. So in a one packet there are two defective plates, and it will give probability of x is equal to 2. And from the Poisson distribution, and it will be e to the power minus 0.02 into 0.02 whole square by 2. And from this we will get the value of the probability. The probability that one packet contains two defective plates, and it will give 0.00019604, and therefore the number of plates in the consignment, and it will give, that means in a 10,000 packet, and it will give 1.9604, and it is equivalent to 2. So therefore the number of packets will contain for two defective plates, and it will give 2. Okay. So after that we are going to take one more examples on the Poisson distributions. If a random variable has a Poisson distribution such that probability of 1 is equal to probability of 2, then find mean of the distributions, standard deviations of the distributions, and third one it will be probability of x is equal to 4. So in that problem there are three parts. So first of all we are going to find the mean of the distribution. So this is the Poisson distribution, and x is the variate. Then the probability mass function of x, and it will give probability of x is equal to I. So this is the probability mass function, e to the power minus mu, mu to the power I by I factorial, where I is equal to 0, 1, 2, 3 and up to infinity. Okay. So as you know, probability of 1 is equal to probability of 2. So this is given. So e to the power minus mu into mu is equal to e to the power minus mu into mu square by 2 factorial. So at p is x is equal to 1, and the Poisson distribution will reduce to e to the power minus mu into mu to the power 1 by 1 factorial, and at x is equal to 2, and it will give e to the power minus mu square by 2 factorial. So after simplifying this equation, and from this we will get the value of mu, and mu is equal to 2. So the mean of this distribution is 2, and the variance as well too. I have already mentioned in the theorem of Poisson distribution, where mu is a mean as well as mu is a variance of a Poisson distributions. So from this we will get the variance is 2 as well, and therefore the standard deviation, and it will give positive root of variance, that means root over of 2. And probability of x is equal to 4, and it will give, if we put I is equal to 4, and from this we will get e to the power minus mu into mu to the power 4 by 4 factorial. That means e to the power minus 2 into 2 to the power 4 by 4 factorial, and from this we will get 2 by 3 into e to the power minus 2. Okay. So this is the probability distribution at x is equal to 4. So after that we are going to take one more example on Poisson distributions. Find the probability that at most 5 defective fuse will be found in a box of 200 fuse. If experience shows that 2% of such fuse are defective. So here is the solution of the given problem. Let capital X denote the number of defective fuse in a box. Then clearly X has a binomial distribution with parameters n is equal to 200 and p is equal to 2 by 100, that means 1 by 50. Okay. So therefore mu is equal to, so in the in that case where n is the very large quantity and p is very small, So NP is equal to the average or moderate fixed value, and we can use the, so from this we will get the Poisson distribution from binomial distributions. Okay, so where mu is equal to n into p. N is a very large quantity and p is a very small. So our n is equal to 200 and p is equal to 1 by 2. So from this we will get the parameter mu on a Poisson distribution, and it will give 4. So using the approximation by the Poisson distribution, and we have probability of x less or equal to 5. So actually from this problem we are going to find the probability that at most 5 defective fuse will be found in a box. So that is probability of x less or equal to 5, and it is equals to summation over I is equal to 0 to 5 e to the power minus 4 into 4 to the power I by I factorial. This is the probability mass function of the Poisson distribution. So from this we will get e to the power minus mu into, if we put I is equal to 0 we will get 1, I is equal to 1, get 4 by 4 factorial. After taking e to the power minus 4 as a common, and then from we get 1 plus 4 by 4 factorial plus 4 square by 4 factorial, 4 square by 2 factorial, and up to 4 to the power 5 by 5 factorial, and from this we will get 0.785. Okay, so this is the required probability of at most 5 defective fuses will be found in a box of 200 fuse. Okay, so I'll stop here. Thank you.